An ideal diode is a perfect switch that lets current flow in one direction with zero resistance, and blocks it completely in the opposite direction. Its IV curve looks like a right-angle corner. For forward voltage V greater than 0, the current I can be any positive value, the line is vertical at V equals 0. And for reverse voltage V less than 0, the current is exactly 0, the line is horizontal on the voltage axis. Because a perfectly vertical line is impossible to draw on paper, engineers use a piecewise linear model. Region 1 reverse bias, I equals 0 for V less than 0. Region 2 forward bias, I equals V minus Vf divided by Rf for V greater than or equal to Vf, where Vf is the forward turn-on voltage often taken as 0.7 V for silicon, and Rf is a small resistance representing the slope of the curve after conduction starts. This model keeps the math simple while still capturing the key behavior: no current when reverse biased, a sudden jump to a fixed voltage when forward biased. An everyday analogy is a one-way turnstile at a subway station. When you push from the allowed side, it rotates freely, no resistance, after you push past a small step the turnstile's arm, but if you try to go the opposite way, it won't move at all. Real diodes do not turn on instantly. Their forward current follows the Shockley diode equation. I equals I sub S times e to the power of Vd divided by NVT minus 1. Where I is the diode current. V sub D is the voltage across the diode. I sub S is the saturation current, a tiny current that flows when the diode is reverse biased, often 10 to the minus 9 amperes to 10 to the minus 12 amperes for silicon. V sub T equals K times T divided by Q. It is the thermal voltage, approximately 25.85 millivolts at 300 Kelvin. N is the ideality factor, 1 less than or equal to n less than or equal to 2, that accounts for recombination and material imperfections. The ideality factor tells us how close the diode is to the ideal case, n equals 1. If n equals 2, the exponential rise is less steep, meaning more voltage is needed to achieve the same current. Think of the diode like a rubber band that stretches exponentially. The more you pull, increase voltage, the faster it stretches current. The ideality factor is like the stiffness of the rubber. A stiffer band, n near 1, stretches quickly. A looser one, n near 2, stretches more slowly. In practice, for Vd greater than about 3 V sub T, approximately 75 millivolts, the minus 1 term becomes negligible, and the equation simplifies to I approximately equals I sub S times e to the power of Vd divided by NVT. This relationship explains why a small change of about 60 millivolts in forward voltage can change the current by a factor of 10 for silicon diodes when n is approximately 1. When a diode is reverse biased, the anode is more negative than the cathode. It ideally should block all current, but two important non-ideal behaviors appear. Leakage, also called reverse saturation current, I sub R, is a tiny current caused by minority carriers thermally generated in the depletion region. It follows the same Shockley equation as forward current but with a negative voltage, so I sub R is approximately negative I sub S. The magnitude equals the saturation current. In most silicon diodes, this is a few nanoamps at room temperature, but it grows exponentially with temperature. Breakdown: if the reverse voltage exceeds a certain limit, the diode conducts heavily. Two mechanisms dominate. Zener breakdown, dominant below about 5 volts, a strong electric field forces electrons to tunnel across the narrow depletion region. This is a quantum effect and is relatively temperature stable. Avalanche breakdown, dominant above about 5 volts, carriers gain enough kinetic energy to ionize atoms, creating a chain reaction of carriers. Avalanche breakdown voltage changes noticeably with temperature. The voltage at which breakdown starts is the breakdown voltage, V sub Br for a Zener diode. This voltage is deliberately set, for example 3.3 volts, 5.6 volts, and the device is used as a voltage reference. An everyday analogy: think of a dam, the depletion region. Under normal reverse bias, only a trickle of water leakage sees through. When the water pressure reverse voltage becomes too high, the dam either cracks, Zener tunneling, or the water forces a sudden flood, avalanche, letting a large flow through. The key takeaway is that while an ideal diode would stop all reverse current forever, A real diode eventually lets current flow either through tiny leakage or a well-defined breakdown point. The dynamic small signal resistance, R sub D, describes how a diode's voltage changes for a tiny change in current around a bias point. Mathematically, it is the derivative of the IV curve. R sub D equals dV over D I evaluated at I equals I sub 0 equals NV sub T divided by I sub 0, where I sub 0 is the DC bias current flowing through the diode. This expression comes from differentiating the Shockley equation and ignoring the -1 term for forward bias. Small signal equivalent circuit. A DC voltage source representing the bias point V sub D0. A resistor R sub D in series with the diode symbol, representing the incremental resistance. Often a parasitic capacitance C sub J is added parallel to the diode to model the charge storage in the depletion region, important at high frequencies. The model looks like a real-world spring damper system. The spring constant, R sub D, tells you how much force voltage you need for a tiny displacement current change. If you tap the system lightly, small signal, the spring's stiffness dominates. If you push hard, large signal, the spring stretches non-linearly and the simple model breaks down. Engineers use R sub D to analyze circuits such as RF mixers, small signal amplifiers, and diode detectors, where the diode operates around a fixed bias point and only tiny variations are important. Almost every diode parameter shifts with temperature, because the semiconductor's carrier dynamics are temperature dependent. Forward voltage, V sub F, for silicon, V sub F drops about -2 millivolts per degree Celsius. This happens because the thermal voltage V sub T equals KT divided by Q increases, with temperature reducing the required barrier height. Example: a diode with 0.7 volts at 25 degrees Celsius will be roughly 0.62 volts at 75 degrees Celsius. Saturation current, I sub S, increases exponentially with temperature. I sub S proportional to T cubed e to the minus E sub G over KT, where E sub G is the band gap energy. A rise of 10 degrees Celsius can increase I sub S by a factor of 2 to 3, which in turn raises leakage current and reduces V sub F. Breakdown voltage, V sub BR. For Zener, breakdown V sub BR is fairly stable coefficient, approximately -2 millivolts per degree Celsius for low voltage Zeners. For avalanche, breakdown V sub BR increases with temperature approximately plus 0.5 volts per degree Celsius, because carriers need more kinetic energy to ionize at higher lattice vibrations. A good analogy is a rubber band. As it warms, it becomes more stretchy, lower voltage needed to push current, but it also leaks more tiny currents appear. Designers must therefore derate diodes at high temperature, provide heat sinks, or include temperature compensation circuits. V sub F of T is approximately V sub F, 25 degrees Celsius minus 2 millivolts times, open parenthesis T minus 25 close parenthesis. I sub S of T is approximately I sub S 25 degrees Celsius times e to the power open parenthesis E sub G divided by K close parenthesis open parenthesis 1 over T sub 25 minus 1 over T close parenthesis, where T and T sub 25 are absolute temperatures in Kelvin. An ideal diode would have no power loss because it either conducts with 0 voltage drop, 0 power, or blocks with 0 current, also 0 power. Real diodes, however, dissipate power mainly in two ways. Conduction loss: when forward biased, the diode drops a voltage V sub F, approximately 0.6 to 0.8 volts for silicon. The power dissipated is P sub F equals V sub F times I sub F. For example, a 1 ampere current through a silicon diode yields about 0.7 watts of heat. Reverse breakdown loss: in reverse breakdown, the diode clamps voltage at V sub BR while letting a large current flow. Power is P sub R equals V sub BR times I sub R. Zener diodes designed for regulation often operate in this region, so their power rating, for example 500 milliwatts, is critical. Maximum ratings datasheets list. Maximum forward current I sub F max is the highest continuous current the diode can handle without overheating. Maximum reverse voltage V sub R max is the highest reverse voltage the diode can block before breakdown, unless it's a Zener. Maximum power dissipation, P sub D, is the total heat the package can safely disperse, often limited by the thermal resistance theta sub Ja degrees Celsius per watt and ambient temperature. Designers use the thermal equation. T junction equals T ambient plus P sub D times theta sub Ja, and must keep T junction below the diode's rated maximum, usually 150 degrees Celsius or 175 degrees Celsius. If the calculated temperature exceeds this limit, a heat sink or a diode with a lower theta sub Ja is required. In contrast, the ideal diode would have infinite current capability and zero power dissipation, which of course never happens in reality. Practical devices are always constrained by material heating and package thermal limits. Different diode families try to approximate the ideal switch, but each adds its own quirks. PN standard silicon behaves like an ideal diode with a fixed V sub F approximately 0.7 volts. Typical forward drop 0.6 to 0.8 volts. Key non-ideal traits are leakage current temperature dependent V sub F finite R sub F and breakdown at approximately 50 to 600 volts. Schottky has very low forward voltage approximately 0.2 to 0.4 volts, closer to ideal less loss. Typical forward drop 0.2 to 0.4 volts. Key non-ideal traits are higher reverse leakage microamps to milliamps, lower reverse breakdown voltage approximately 20 to 30 volts, and no significant Zener effect. Zener is intended to operate in reverse breakdown, deliberately not ideal in forward direction. Forward voltage same as PN approximately 0.7 volts. Key non-ideal traits are well-defined VZ stable, with temperature for low voltage Zeners controlled reverse breakdown, higher dynamic resistance in reverse region. LED emits light when forward biased. Forward voltage varies with color 1.8 to 3.5 volts. Typical forward drop 1.8 to 3.5 volts higher than ideal. Key non-ideal traits are significant forward voltage non-linear, IV temperature-dependent color shift, limited reverse voltage approximately 5 volts. Analogies. A standard PN diode is like a regular door that opens only one way and needs a small push to swing. A Schottky diode is a sliding door that opens with almost no push low V sub F, but leaks a bit of air higher reverse leakage when closed. A Zener diode is a pressure release valve. It stays closed until the pressure reverse voltage reaches a set point, then it opens to keep the pressure constant. An LED is a one-way door that also flashes a light when open. The extra energy needed to create light makes its forward drop larger. All of them deviate from the ideal model in predictable ways, and engineers choose the type that best matches the required trade-off between voltage drop, speed leakage, and breakdown behavior. Problem 1. Piecewise linear versus Shockley. A silicon diode conducts 10 milliamperes in forward bias. Using the ideal piecewise model, V sub F equals 0.7 volts, R sub F equals 0 ohms, find the voltage across the diode. Then, using the Shockley equation with I sub S equals 10 to the minus 12 amperes and N equals 1, calculate the more accurate forward voltage. Solution: ideal model, V sub D equals 0.7 volts. Real model, V sub D equals NVT times natural logarithm of open parenthesis I divided by I sub S plus 1 close parenthesis. Approximately 25.85 millivolts times natural logarithm of open parenthesis 0.01 divided by 10 to the minus 12 close parenthesis. Approximately 0.65 volts. The difference shows the ideal model overestimates V sub F for moderate currents. Problem 2. Small signal resistance. A diode is biased at 5 milliamperes. Determine its dynamic resistance R sub D, assuming N equals 1 at 300 Kelvin. Then draw the small signal equivalent circuit. Solution: R sub D equals NVT divided by I equals 25.85 millivolts divided by 0.00. 5 amperes equals 5.17 ohms. The equivalent circuit is a voltage source of 0.65 volts bias in series with a 5.17 ohm resistor, plus junction capacitance if high frequency. Problem 3. Reverse breakdown rating. A Zener diode is rated 5 volts Zener voltage. I sub Z max equals 20 milliamperes and P sub max equals 0.5 watts. If the supply is 12 volts, and the series resistor is 350 ohms. Calculate the Zener current and verify that the power rating is not exceeded. Solution: the Zener voltage clamps at 5 volts, so the voltage across the resistor is 12 volts minus 5 volts equals 7 volts. Current equals 7 volts divided by 350 ohms, approximately 20 milliamperes. Power in Zener equals 5 volts times 20 milliamperes equals 0.1 watts, which is less than 0.5 watts, so it is safe. The problem checks understanding of reverse breakdown operation versus ideal infinite breakdown voltage.